In the previous video I showed some of the geometry plotting capabilities in Serpent along with new features introduced in version 2.2.2 which was released last month. In this video I'll do the same for the mesh plotter, and what is common between these two features is that they've been both around since the early days of Serpent development, and both include a lot of capabilities that are not widely used, mainly because of the complicated input syntax. And in the latest update we added these new input cards to simplify the use of these advanced features. So what are mesh plots in Serpent? At its most basic form, the mesh plotter produces these dual color images which show the fission rate distribution in hot colors or shades of reds and yellows, and thermal flux in areas where there's no fissile material in cold colors or shades of blue. And these are very Serpent specific images, and whenever I see something like this I immediately recognize that this was made using Serpent. Creating these basic mesh plots is simple. You just define the orientation and the PNG image size in pixels. So if you're working with a thermal reactor system, this is a really convenient way to visualize what's going on. You can also easily select a plotted range using this 3D bounding box with the mesh input card, and by default the mesh is bounded by the geometry outer boundaries. The only annoying part about this default formatting is that the aspect ratio of the produced image, it has to match the aspect ratio of the bounding box, or otherwise the image will be stretched in one of the dimensions. These basic fission rate and thermal flux plots are not very useful for fast reactors because they show the fission rate distribution without any flux, simply because there's no thermal component in the flux. And for non-reactor applications, like if you have photon transport simulations, they won't produce any output at all. And for this reason the mesh plotting capability was later extended to detectors, so that you can plot whatever is scored in your standard detectors that are based on the collision flux estimator. When we started getting users from the Fusion community, we also implemented this cylindrical mesh plot feature that allows generating these distributions with rotational symmetry as you would have in toroidal Fusion devices. Adding these new features eventually made the mesh card syntax very complicated, as you can see in this description at the Serpent wiki. So in the latest version 2.2.2 we introduced this new mplot input card that instead of listing a long line of arguments uses these optional parameters in a more intuitive format. And it also includes some new features that are not available in the old mesh card. So this is basically a similar kind of addition as we did for the new gplot card to geometry plotting capabilities that I talked about in my previous video. Before diving into the new input card and the new features, I'll explain a bit how the mesh plotter actually works. So the mesh plotter sees the collisions that occur during the particle random walk, and these are the same collisions that are used to produce all the Monte Carlo results estimates. The mesh plot defines a volume, and the scores from collisions inside that volume, they are projected to a plane. So basically a 3D distribution is collapsed into a 2D matrix that is then used to generate this PNG image. Like all volume-based Monte Carlo estimators, the results represent integrals over the phase space variables and time. So the fission rate, which is the distribution that you see in the hot colors in the default mesh plot, can be formally written as an integral like this, and the thermal flux like this. So you have integration over energy limited to the thermal group here. For the more general detector plot, the response function depends on the dr parameter of the detector card and also on the integration limits they depend on how the parameters are set in the detector card. A couple of notes. The mesh plot shows only what the detector scores. So if you calculate a reaction rate in some specific material, the plot will only show scores or the reaction rate distribution in that material. Also, all the detector scores are shown in the same plot. So even if you have something like energy binning or multiple cell bins or mesh bins, they all end up in the same image. So the difference to detector output is that if you calculate some reaction rate inside a cell using a detector, you get a single value in the output that represents the volume averaged reaction rate inside that cell. If you use this same detector to produce a mesh plot, what you get is the distribution of scores in the mesh plot. So the volume averaging is basically done at the resolution of the individual pixels, which are collapsed in one dimension. A couple of more things that were also addressed in the new Serpent user guide. Now, because these mesh plots, they are collapsing a 3D distribution inside a volume into a two-dimensional image, they work best for 2D geometries where the distribution is uniform in the collapse direction, like 2D fuel assemblies, for example. For 3D geometries, the produced images can sometimes be a bit misleading. Like here's an example from a high-temperature gas-cooled reactor pebble calculation. So the pebble has 15,000 of these microparticles inside it, and as you can see in the geometry plot, there's quite a lot of space between these particles. The packing fraction here is only around 9%. But then when you make a mesh plot out of this calculation, the mesh plot looks like it's fully packed because everything is flattened into one dimension. Another thing to note is that the color scales in the default plot are linear, and they are normalized in a way that works for most thermal reactor geometries. In some cases, there's just too much variation in the flux levels that the linear scale doesn't really capture the highs and lows, and you get these images that can seem like they are overexposed or something like that. So this example here is from the JHR material test reactor, and the flux level drops by so many orders of magnitude between the center of the core and the outer parts that you would really need a logarithmic color scale to show the variation. So this is what the collision rate distribution in the same reactor looks like on a logarithmic color scale, and as you can see, it shows much more detail in the outer parts. One more note before going into the new mplot input card. I quite often get the question if it's possible to add access, color scales, labels, other information to the mesh plots, and the answer is no. So this is not really what the mesh plots are for. They are meant to give a quick visual of the transport process, so to help the model generation and in general to get a better understanding of what's going on. So if you want to have these publication quality images, you can use the mesh detector capability instead, together with proper visualization tools to plot the results and add labels and any other relevant information. So the new feature in the latest Serpent update is the mplot input card, which provides an alternative syntax for defining mesh plots. It uses the same routines as the old mesh card, which still works for these basic fission rate and thermal flux plots, but for detector plots especially, the new syntax is much more easier to use. And this is also why we left the advanced features out of the old mesh plot card description in the Serpent user guide. So instead of listing all arguments in one line, the mplot card uses these optional parameters. One mistake in version 2.2.2 was that the meshplot name that is used with geometry transformations, it was left as a required argument. It should have been optional like it is for the gplot card, and this is something that we'll fix in the next update. So The basic functionality of this mplot card, it uses these x and pix parameters. So the x parameter defines the plot axis, which is the axis perpendicular to the projection plane, 1 for x-axis, 2 for y-axis, 3 for z-axis, and the corresponding projections would be the yz, xz, and xy planes. If you set this value to 4, it gives a cylindrical plot where the rotation axis is in the positive direction of the z-axis. The pix parameter, it simply defines the image size in pixels. If there's no detector defined, the mplot card produces the standard fusion rate and thermal flux plot, just like the old mesh plot card, or the mesh card. The volume inside which the results are collected are defined using these dim x, dim y, and dim z parameters if you have a Cartesian mesh plot, or dim r and dim h if you have a cylindrical mesh plot. Another parameter that defines a feature that is also in the old mesh card is the sim, which sets the symmetry option. So for some reason, Serpent wiki description says that this feature is not used in Serpent 2, and this is not true. The description of these mesh plot symmetries is now found in the new user guide. In my last video I talked about these pixw and pixh parameters for the new gplot input card, which let you set the image size or image dimensions in pixels in only one dimension, and the other dimension is then scaled automatically to preserve the aspect ratio, and this is a very convenient feature for plots that are not square shaped. So you don't have to calculate the image dimensions to preserve the aspect ratio. Serpent will rather do that for you, and these two parameters are also available in the new mplot card. One completely new feature is the ability to apply geometry transformations, and this is done in a similar way as for the gplot card. So you assign a name for the mesh plot and then reference it in the trans card. So the trans card now also has a new type MPL, which links the transformation to the mesh plot. With this new feature you can do things like rotate the view, and sometimes looking at these collapsed 2D distributions from different angles can give you some extra insight into 3D geometries. This may not be the best example here. Another use for the geometry transformation is that you can shift and rotate these cylindrical mesh plots, which are otherwise centered at the origin and oriented in a fixed direction. What I think is the biggest improvement in the new syntax is how these detector plots are now defined. So there are two key parameters, this DSC and lim parameter. The DSC parameter defines the detector for which these scores are plotted, as I explained earlier in this video, and the color map that's used for the plot. So Serpent provides these 12 built-in color maps, and you can also select whether the scaling is linear or logarithmic. So entering the color map number as a positive value will produce the plot in a linear scale, and if you put the same number with a minus sign, the scaling is then logarithmic. The minimum and maximum values of the color scale are defined automatically based on the distribution, but you can override the default values using this lim parameter. Unfortunately, there's a bug in the way these limits are applied. This bug was discovered right after releasing update 2.2.2. The parameter sort of works, but the way the scaling is done will be a bit different in the next version, and will also include a better description for the parameter then. So to give you a couple of examples, here are a few mesh plots from the JHR reactor test case. So you can also see the input syntax that is used for producing these mesh plots. So this is the standard fission rate and thermal flux plot. This is the neutron density distribution. This is the neutron collision rate. This is the secondary photon source, meaning photons produced in neutron reactions. Photon density. photon collision rate, and photon heating rate. All except the first image were plotted using logarithmic color scale, and for neutron plots I used this jet color map, which is number 4, and for the photon plots I used the blue-red color map, which is number 13. The detector functions can be response functions can be found in the Serpent documentation. Thank you for watching. I'll do another video on visualization features in Serpent next time. So the topic for the next video is track plotting, and after that I'll move to a bit more advanced topics on other features like some less used geometry types, radioactive decay sources, and various reduction capabilities in Serpent, and so on. And if you have any ideas for topics that you would like to see, let me know in the comments. Thank you.